pictures over here a little bit so my notes are visible. Well, thank you all for attending. As it's been mentioned, the title of the talk is Saving the Hubble Telescope, but it could just as well have been Saving NASA. That's how important this mission was to the NASA space program. This talk might be a little different than others that you've heard because the emphasis is on engineering rather than science. The title slide here is the Hubble telescope being released after it was repaired. And I draw your attention to this little white rectangular square here on the side of the telescope. And we'll spend a fair amount of time in the next hour discussing the instrument that's located there. So here's the plan. I'm going to talk in general about the Hubble Space Telescope Observatory. I'm sure many people who are listening in the audience know a lot of details, but just to make sure everyone's kind of on the same page. And then I'll discuss the origin and the nature of the telescope's optical problem. And then a good part of the time, we'll talk about the fix, which for this talk is going to focus on the wide field planetary camera. And I'll also mention COSTAR, which is really part of the whole fix of the telescope. And then I will give a selected science result. So we start with the launch. As Steve mentioned, this is August 24th, 1990, the launch of the Space Shuttle Discovery. So the question is, where is the telescope in this picture? And the telescope is in the cargo bay of the shuttle. Here you see the cargo bay doors are open. The manipulator arm is lifting the telescope out of the cargo bay. The solar panels have already been deployed, and you can see that there is a cover on the telescope. And the reason for that at this point is the cargo bay is considered a dirty environment relative to space. So it's important to keep the optics as clean as possible. And the telescope is thus covered up until it gets far enough away from the shuttle. And here you see it on its own, moving away from the shuttle, and just a gorgeous picture of the telescope on orbit. So HST was designed to be launched and periodically serviced by the space shuttles. So that had a huge impact on just about everything to do with the observatory. And in particular, it set a limit on the size of the primary mirror. Clearly, you want to be able to launch the largest mirror you can. And so they did that. But of course, weight is the most important issue when you're sending something to space. So that limited what could be done. And the shuttle itself has a limited lift capacity. By servicing, we mean that lots of subsystems, batteries, solar panels, gyroscopes, telescope instruments even, were designed from the beginning to be repaired or upgraded or replaced by orbit astronauts working on orbit. And that, of course, took place. There were 5 servicing missions. The one we're going to focus on is the first one, 1993, actually in December of that year, where the repair was taking place. The shuttle program ended in 2011. So the Hubble Space Telescope has been on its own for 11 years now, almost 12 years. And there probably will never be another servicing because there is no shuttle program. And the telescope will hopefully survive on its own for another 10 or 15 years. So the telescope is a large instrument. It's the size of a school bus, weighs 24,000 pounds. It's in what's called a low Earth orbit, which is about 340 miles roughly. The altitude of the Hubble, you'll see different numbers because it's been boosted up at various times. And of course, it slowly decays because there is atmospheric drag where it is. It's moving 17,000 miles per hour and takes about an hour and a half to complete one orbit. So I just want to step through quickly the pieces that make up the observatory. There are two antennae located here and here. You notice they face opposite directions to give more coverage. Solar panels and batteries, which supply the electrical power for the instruments and computers and so forth on board. There's a radiator located under here, which serves this instrument, and which we'll talk about later on. It has three what are called fine guidance sensors. Now, you can see two in this picture, and then there's one along the other side here. They're responsible for the pointing stability of the telescope. And they actually do a remarkable job. That was a whole technological development itself to be able to point the telescope and hold it accurately. Then we have what's normally the telescope itself. It's usually called the OTA in documents, which is the optical telescope assembly. It consists of a primary mirror located here and a secondary mirror located there, and we'll see a lot more about that. And then the science instruments. So basically, a telescope is nothing but a light collector, and then feeds that light to the science instruments, and that's where the real data comes from. There are four what are called axial instruments located in this package here. They're called axial because their optical axis is basically parallel to the telescope's optical axis. And there are four radial instruments. Here's the one we'll talk a lot about, the wide field planetary camera, and then the three fine guidance sensors, which also function as science instruments. They can do astronomy, that is, they can do precise precisioning of stars, which increases the ability to measure parallax of distant stars and help you establish the distance scale. These are called radial because their optical axes are perpendicular to the telescope's optical axis. So here's a cutaway where you could see the telescope a little better. These instruments are more current. Most of these have been replaced, but all the original instruments in the telescope have been replaced. So here's where the axial instruments sit. You can see that more clearly in this one. Here's where the radial instruments sit, and the wide field planetary camera is down here. Here is the primary mirror, and then there's a baffling tube here, and here's the secondary mirror. Also visible in this picture are these rods. These are graphite epoxy metering rods, and their function is to hold the structure between the primary and secondary mirror stable, because obviously you don't want that dimension changing if you can help it. But within that stability, you have freedom to move the secondary mirror. The secondary mirror can be moved axially, which adjusts focus. It can be decentered, and it also can be tip-tilted. So I just list the four axial instruments. As I said, they've all been replaced. There's two spectrographs included, which, as you probably know, a spectrograph is like a prism. It breaks up light into its constituent wavelengths, and a huge amount of information can be gleaned from that. There's a high-speed photometer and a faint object camera. Those are essentially highly sensitive light meters. They don't use the CCDs that we're going to talk about. They use a more sensitive type of tube to count photons, actually. And then the radial instruments, as I mentioned, the wide field planetary camera we'll talk a lot about, and then the guidance sensors. So here is a simplified drawing, in a way, of the telescope. Note it is not to scale. There's only two mirrors. Now, a lot of people might think that the Hubble telescope, being such a sophisticated instrument, has some very complex telescope, but it really doesn't. It has a two-mirror telescope, like many instruments. The primary mirror and the secondary mirror are both hyperboloids, and we'll talk a little bit more about that. So as Steve already mentioned, the primary mirror is 2.4 meters in diameter, which is about 8 feet. It's made of ULE glass, which is sort of a cross between glass and a ceramic. ULE stands for ultra low expansion. It's obviously very important that the mirror remain dimensionally stable. And the same is true of the secondary mirror. The secondary mirror is about 1 foot across. It is made of another low expansion glass, but this one is called Zero Dur. Yeah, this one is a shot glass product, and I didn't mention ULE is a Corning glass product. The separation between the primary and secondary mirror is about 5 meters. Both the primary and secondary mirrors are coated with aluminum and then overcoated with a magnesium fluoride, which increases the reflectivity of UV. One of the unique features about the Hubble telescope, which really isn't discussed very much, the Hubble telescope and its instruments is able to operate in the near ultraviolet, throughout the visible, and into the near IR. It's very unusual to have a platform that can cover all 3 of those spectral ranges. And the UV is particularly problematic, but Hubble was made to observe at those short wavelengths. So I want to talk a little bit more. Whoops, I'm sorry, didn't want to go through this one. I'm going to skip to this slide. I want to talk a little bit more about the mirrors and their shapes. So the primary and the secondary mirror are what are called conic sections of revolution. So you may remember from high school geometry, there are 4 conic sections. That's what you get if you take a cone and slice it at different angles. You can get a circle, you can get an ellipse, you can get a parabola, and you can get a hyperbola. Then if you take one of those things, like let's say a parabola, and you rotate it around its axis of symmetry, you get a solid, a 3-dimensional figure, which we'd call a paraboloid. And most telescope mirrors are one of those things. They're either spherical, which comes from the circle, or they're elliptical, ellipsoids, or paraboloids, or hyperboloids. And the thing about these conic sections is their surface figure can be described by 2 numbers. One is called the radius of curvature, which I denote as R, and one is called a conic constant. So it's not critical that if you're not familiar with this, that you understand exactly how those numbers come in. You can just think of them as 2 parameters that are used to define and design the shape of the mirrors. So here are these parameters that are for the primary mirror. The radius of curvature is about 11 meters. The primary mirror is, of course, concave. And the primary mirror has a conic constant that's just a little less than -1. And that makes it a hyperboloid. The secondary mirror is convex. That's why there's a minus sign here. And it's also hyperboloid, but you can see it's -1.4, which means it's more strongly hyperboloid. And we'll come back to these numbers. This one is in red because that's the critical number that affected the telescope. So here we see the primary mirror on a polishing table where it was manufactured at Perkin-Elmer in Danbury, Connecticut. The primary mirror, of course, is not just this top sheet here. And here is a note. Also, I want to point out the central opening, which we'll see more about. But here you get a better view of the primary mirror. It's uncoated at this point, so you can see through the glass surface into the structure in the mirror. It's light-weighted, which reduced the weight from 8,000 pounds to 1,800 pounds. Again, weight is everything when you're putting something in space. So this mirror, you could see the structure. It's got a fairly thin top sheet here and a fairly thin bottom sheet, and in between you have this thick honeycomb structure which provides the stiffness for the mirror, and at the same time allows it to be light-weighted. And this is a good view of the opening in the center here. Well, after the mirror is coated, it looks like this. You could see the mirror in its handling fixture. This is in a very clean environment. As we mentioned, contamination on the mirror surface is very critical. So this room has filtered air. You could see all the technicians are dressed in what are called bunny suits to prevent contamination from clothes and skin and hair. Here's the central opening, which is covered by an aluminum plate at this point. And take note of these 3 points here. Those are the mounting points, and we'll see a little bit more about them shortly. So, as Steve mentioned, the Hubble primary mirror was the smoothest, cleanest optical mirror ever manufactured. It was the most accurately shaped optical telescope mirror. However, I did include this caveat. I believe that was true at the time it was fabricated, which was somewhere in the late 80s. Okay, so we're 35 years ago. I don't know in that intervening time if that's still the case. Wouldn't surprise me if it was, but it was certainly at that time. So there was an exceptionally excellent mirror manufactured, but everyone knows it had a problem. And the problem was that the mirror was fabricated to the wrong shape. So even though it was shaped accurately, you can think of it as the template they used to shape it was not the correct one. So they got this fantastic mirror, but it's got the wrong shape. So how was this error actually discovered, and what was the cause of it? Well, here's an image taken sometime in the early days after the telescope was launched. It was launched in April. And of course, they did a lot of tests between April and June. And this is what a typical stellar image looked like during this period. About 15% of the starlight ended up in an enclosed circle of 0.1 arc seconds, which is, of course, extremely small area, but that's what you want. You want a well-focused image of a star. The specification was that 70% of the stellar energy should end up in that 0.1 arc second circle. And as you can see, all the energy that didn't go into the central image ended up getting smeared around in this very elaborate looking halo. And if you look at the halo carefully, you'll notice there certainly are these 3 points here which stand out. Those are the mounting points of the primary mirror. In other words, part of the image here is so out of focus, you're actually looking at the primary mirror as well as looking at this distant star. So it was clear right away that there was a serious problem. They tried to fix it, or at least tried to narrow down what the issue was by adjusting the focus. They tried tilting the secondary mirror. They tried decentering it. And after this 2 months worth of tests, it was very clear there was an unfixable problem. That is, no adjustment was going to improve the image. The immediate suspect was the primary mirror. So this was in June 1990. So immediately NASA came up with a plan to figure out what was going on. This was called the Hubble Aberration Recovery Program, or HARP. In order to fix the telescope, you have to understand exactly what the nature of the optical problem is. So when you go into the optometrist and tell him you're having trouble reading, what does he do? He sits you down and he puts a bunch of lenses in front of your eyes and he says, better or worse? And he keeps doing that till he figures out, okay, here's the problem with this guy's lenses in his eye, and I know how to fix it. So we had to try and do the same thing with Hubble, but from 300 miles away. NASA funded 2 avenues of investigation. The first I call the fabrication study. So they went back to Perkin-Elmer They had to examine all the tooling that was used in the fabrication, all the optical instruments, laboratory logbooks, talk to all the technicians, all the optical engineers, anyone who was associated with the production of that primary mirror, and see if they could figure out what happened. At the same time, there was an analytic study going, and that consisted of about 10 or 12 teams across the country, basically working independently, using, for the most part, they were using detailed optical computer models and tried to reverse engineer the telescope and the wide field planetary camera, which was producing those images, to see if they could reproduce the on-orbit stellar images. What did they have to change in the prescription of the telescope and the camera in order to reproduce those images? NASA said, we're only gonna believe that you guys have figured out what the problem is if these two avenues of investigation agree. And the term agree was a little bit fuzzy, but here's what happened. So before I show you what the results, here's what the modeling can do. Very sophisticated computer models that actually, this image was even developed after the telescope was fixed. They continued to analyze the images and trying to improve their models. So here's what the observed image looked like. We saw something like that already. And here's produced by the model. And you can see that the diffraction effects, which are caused by the spiders holding the secondary mirror and other obstructions, and also in this case, because the images got a lot of aberration, you see parts of the primary mirror, and there are also something called zonal errors produced when the mirror is fabricated, and you can see all these rings here. All that was incorporated in the model, and you can see it's just an astounding amount of detail is reproduced. So it gave them a lot of confidence that the model was correct. So here are the results of this study, which went on for quite a few months to try and figure out what the as-built elements were, and particularly the primary mirror, which, as I said, was suspected from the beginning. So they were particularly interested in trying to figure out the conic constant. You remember I said that was one of the two parameters that is used to describe the surface. The fabrication study came out with a number -1.013. The analytics study came out with -1.014. So they're very, very close. And again, it gave people confidence that they understood what was going on. Furthermore, the studies indicated that the secondary mirror of the telescope and the science instruments, in particular the wide field planetary camera, were all built to specification. So the outcome of the study was that the only real problem is with the primary mirror, and we think we know what it looks like. Just to compare that, as they continued, even after the telescope was repaired, continued to study the problem, the current best estimate for this conic constant for the primary mirror, as you can see, is extremely close to the analytic study back in 91, and not too far from the fabrication study. Compare that to what the design was. So it's off by about 1.2%, which doesn't sound like a lot, but was catastrophic. In optical terms, this kind of an error produced spherical aberration in the wavefront coming from the telescope. So everybody agreed at this point. We know what the problem is. We have confidence in it. Before I jump ahead, let me just say a word about the spherical aberration, because this may not be familiar to everybody. This is just a cartoon, by the way. So in the bottom picture, you see rays coming in from a star. They're parallel because the star is essentially infinitely far away as far as the optical system is concerned. And all the rays, no matter where they strike the mirror, come to a single point for a focus. And that's as it should, because now the image is a point and the object is a point, it's a star, so everything is as it should be. When the mirror has spherical aberration, which you can see by this surface here being added to the perfect mirror, where the rays come to focus is a function of how far those rays strike the mirror from the center. So out here on the edge, you could see the rays are coming in here short. And when the rays are striking toward the center of the mirror, they get focused further out. And the issue there is, where do you put your detector? Anywhere you put your detector here, some rays are going to be in focus and you're going to see a nice sharp image, and some rays are out of focus and you'll see this halo of light. So there's not much you can do. It's a function of the fact that the mirror has the wrong shape. The question is, how did that happen? If this was such a carefully fabricated mirror, how could that have happened? Well, I call this nothing comes for free. And the reason I say that is these aspheric mirrors, which perform much better than spherical mirrors as far as image quality over a wide field, are more difficult to test. So there's always a catch somewhere, right? And to test this primary mirror, Perkin-Elmer designed a special optical instrument that's called the reflective null corrector. And it was built and designed and built to guide the fabrication of the primary mirror. Simply put, this tooling, this optical instrument projects, I call an optical template. It's a wavefront that has the desired aspheric shape that they want the mirror to take on. And you put it in a test fixture with the mirror and you're able to monitor the surface of the primary mirror and see if it's doing the right thing. So this reflective null corrector is actually a fairly simple device. There's a lot of lines here, but those are just some ray tracing. It consists of three optical elements. There is an upper spherical mirror with a hole in it. There is a lower spherical mirror with a hole in it, and then there's a lens. So you project a point source here, which reflects off the lower, off the upper, comes down through the lens, and eventually will spread out and strike. Here's the primary mirror under test. When the wavefront matches the surface of the mirror, these rays will reflect back on themselves. They'll retro-reflect, go back through the system and come here and form a point image. So that's the way you can tell whether the mirror has the proper shape with regard to the wavefront that they're projecting. So putting the reflective null corrector, even though it only has three elements, putting it together is quite critical. You want the spacing of the elements to be very precise so that the wavefront it projects is equally accurate. In particular, we're going to look at the spacing of this lens down here from the center of curvature of the lower spherical mirror. So since this is a part of a sphere, clearly there is a center of curvature here. The spacing was determined by an INVAR metering rod. INVAR is a metal, composite metal that is very insensitive to temperature change. So once they set the length of that thing, it's going to change length with temperature only by a minute amount. And that's the kind of thing you want as a measuring tool. So the idea was you put the top of the rod at the center of curvature, and you put the vertex of the lens at the other end of the metering rod. Well, sound like a good idea. Let's look a little more closely at what they wanted to do and what actually happened. So from an interferometer, they produce a focus beam that is supposed to come down on the tip of the rod. And just like with that we were talking about with the primary mirror itself, it will retro reflect back. And when it does that, you know that the metering rod is in its right position. And in order to be more careful, you always got to be aware, however, when you're more careful, you don't screw things up, they put a cap on the top of the metering rod, and they painted the top surface of that cap an absorbent black. So they would only get a reflection back when this focus beam hit the top of the rod. That was the plan. So what actually happened? Well, the metering rod was okay. The cap, unbeknownst apparently to anybody, had a chip in the surface here where the paint was supposed to be. In other words, there was a somewhat reflective surface on the cap. And when they were trying to position this focus beam here, it got focused on that reflective part of this cap and sent the beam back, and that they believed was coming from the rod. You could see here there was a 1.3 millimeter displacement between the top of the rod and the top of this cap. So that pushed the lens 1.3 meters further away from the position it should have been in. Well, this was a disaster, it turns out. In fact, the spacing error of the lens was so much different than the design was that they had to insert an extra spacer to install that lens. Because 1.3 millimeters is a huge error when you're putting together optical elements. So this, in a nutshell, is why the primary mirror ended up with a wrong shape, because this instrument, this reflective null corrector, which was supposed to monitor that shape, was not put together correctly. Well, what lessons can be learned from this? I call this a textbook case of what not to do. There are tons of lessons learned. If you read the various reports that came out about Hubble, just tons of stuff that was criticized. So I tried to just summarize it into two categories: engineering issues and management issues. So in the engineering category, this reflective null corrector was a single point failure in the sense that Perkin-Elmer had great confidence in this instrument. It was specially designed to be accurate enough to do this job, but there was no independent testing once the thing was put together that it was done properly. In fact, two auxiliary measurements with cruder instruments showed that there was a problem with the primary mirror before it left the factory. Instead of going back and trying to resolve the issue why certain instruments did not agree, they chose to just accept the results of the reflective null corrector because that was the expensive, well-designed, carefully implemented instrument, and ignored these other results. The fact that it required an extra spacer when it was put together also seemed to have eluded attention. Normally in that case, if you're following a procedure and you have to do something that's not in the procedure, you stop. The technicians doing the work should have consulted with optical engineers and figured out before they continued what the issue was. None of that was done. The other was a sort of a functional problem, that the optical engineers were in one organization and the technicians putting the reflective null corrector together were in another organization. There was not good communication. Management, well, as I've already sort of pointed out, Perkin-Elmer had insufficient oversight or independent review of this whole fabrication process. And management accepted risks. This would be NASA management, accepted risk, but really didn't follow up with supervision. Now, what do I mean by accepted risk? Okay, NASA has a policy that you test as you fly. If you're going to fly an instrument, You want that instrument assembled on the ground, and you want to completely test it as it's going to be in space. In this case, it was difficult. It's very expensive to produce a test setup for a fully up Hubble telescope. And because the Hubble telescope primary mirror is so accurately fabricated, you need an equally well-fabricated flat mirror to test it. And this is, for a mirror that size, is a very expensive issue. So NASA accepted the risk. We'll build these two mirrors, the primary, the secondary, separately. We'll test them separately. If they look good, we'll put it together and assume it'll work. And the reason that these compromises were made is that PerkinElmer and NASA were under severe cost and schedule pressures. Hubble had a very checkered history of funding. It was on, it was off. And so people were feeling the pressure to get it done and get it in space. When you do that, problems occur. Okay, so they figured out the exact problem with the telescope. The question is now, what do we do? How are we going to fix this thing? There were many ideas sent in what should be done. A lot of them were pretty nutty, but turned out that the solution that we ended up using was already under works at the Jet Propulsion Laboratory. Here's a picture of the laboratory in Pasadena with the San Gabriel Mountains in the background. Here's the wide field planetary camera being installed in the Hubble telescope before launch. This camera was built by JPL, and it was the prime imaging instrument that went along with Hubble. However, 6 years prior to Hubble's launch, JPL was already building a copy of that camera called WIFPIC-2. There were several reasons for that. 90% of Hubble's scientific data was going to be generated by the wide field planetary camera. And they knew the spectacular images it returned would have great public appeal, which of course is always good to keep funding going. The public sees these these great images, they get excited and keeps the project going. The images are also used to point the spectrographs on the telescope. And finally, the original wide field planetary camera had been built with very little redundancy, so it made sense to have a copy. And another reason, which I didn't list here, is that there were several upgrades. That even though the camera is basically the same, they improved a number of things, particularly the detectors. The CCDs had advanced in that time, and so they were used more sensitive detectors. But I should point out, even though there was a little redundancy in the wide field planetary camera, that during its 4 years on orbit, there were no failures. So that was never the issue. So in the next few slides, I want to describe in some detail how the camera works in order to lay out how the fix was implemented. So here is a kind of array diagram of what I call it one of the single channel of the camera, and I'll explain that in a moment. So the light comes in from the telescope, and there's what's called a pickoff mirror, which sends the light from part of the focal plane of the telescope into the camera. So if you're familiar with a Newtonian telescope, this is just like a Newtonian telescope that has a flat mirror. The light passes through a shutter and a series of filter wheels, strikes what's called the pyramid mirror. Now, the pyramid mirror is a four-faceted mirror. The surfaces are flat mirrors. And what it essentially does is it divides the light coming from the camera field of view into four pieces, four quadrants. And each of those four quadrants goes through an optical channel like this. So they're identical. There's one up here, and then the facet down here would reflect to the same setup, but is the mirror image down here. And then the two other facets would reflect to optical paths like this that are in and out of the screen. So altogether, there are 4 of these relay channels in the camera. Now, why do they do that? I mean, it seems like an extra complication to have to build 4 of these things. Why don't they just have 1? And the reason was this camera is supposed to have a wide field of view. But when the camera was being designed and built in the mid and late 80s, wide format, large format CCDs were not available. So these CCDs that go in each of one of these camera heads is an 800 by 800 pixel, which is, you can see, very small by today's standards. They're 15 microns on square. So in order to be able to see a larger portion of the sky, they said, let's make 4 images and we'll stitch those images together to see as much area as we want. So that's the reason there are these 4 channels. Now, this is a flat mirror, this is a flat mirror, so they don't really do anything except redirect the light into this relay. And the reason, it looks like a little Cassegrain telescope. It's got a primary and a secondary. And the purpose of the relay and why it's called a relay is it takes the image that the telescope forms, here's the focal plane of the telescope, and relays it to the CCDs. So why did they do that? Because this allowed them to change the magnification from what the telescope would have given. So essentially, this relay decides what the magnification will be. And as I said, there are 4, I'm talking about 4 channels here. Now, let me show you how this is all implemented in hardware. So I'm just going to go through the same sequence. Here's the light coming from the telescope. It hits the pickoff mirror, goes through the shutter and filter wheels to this point, which is the pyramid mirror. Unfortunately, it doesn't show up very well. And that's where the field is divided into 4 parts. It reflects it off the pyramid mirror up to these fold mirrors, then back through holes in this bulkhead. And you can see, well, barely see these 4 beams. And they go into these light baffles, into the relays, back here to the camera heads. And then there's a radiator to cool the CCDs, which keeps the noise down. Now, if you look at this diagram carefully, you see, well, here are the 4 holes that are being used, but then there's 4 other holes that don't seem to be used for anything. And it seems like there's a relay here that's not doing anything. I don't see any light going into it. And the reason is the camera actually has 2 magnifications. So it's as though you had a camera and you changed lenses. You can adjust the magnification, if you will. In the wide field mode, the pixel scale, each pixel is worth 1/10 of an arc second on the sky. And just to give you a feel for what 1/10 of an arc second is, it's the diameter of Pluto as seen from the Earth. So it is a very small angular subtense on the sky, and in the wide field that's per pixel, but you can even do better than that. If you switch to the planetary mode, then it's about 2.5 times finer. That is 0.043 arc seconds per pixel. So you see a smaller portion of the sky, but you have more detail because the pixels are finer on the sky. So you have these 2 modes. Each one of those modes has 4 channels, as I explained, so that you could have stitch those 4 together to get the full image. And each one of these channels leads to an 800 by 800 CCD. So how do you switch between these 2 modes? Well, you recall that pyramid mirror. That pyramid mirror is actually capable of rotating. You can rotate it by 45 degrees. And what that does is it moves the light from one set of 4 channels to a different set of 4 channels, which has a different magnification. So it's a little complicated. I know this is a lot of stuff I'm throwing at you, but maybe this will help make it look clearer. This is what the field of view of the camera looks like on the sky. So when you're in the wide field mode, here are the 4 channels. Each one is an 800 by 800 CCD with that 0.1 arc second per pixel. And that's what your image would look like. When you rotate the pyramid mirror 45 degrees, it switches the light into another 4 channels when the only difference is the magnification. So here are the 4 planetary channels. Again, this is what an 800 by 800 CCD sees. You see it's a smaller patch of sky, but you get better resolution. And again, just to put this in perspective, this area is about the disk of Jupiter, which is why it's called the planetary camera. And for people who like numbers, this is 160 arc seconds across. And then in the planetary mode, you get 70 arc seconds across on the sky. Here's what the field of view of the wide field planetary camera looks like in the focal plane of the telescope. So the Hubble telescope produces light over this focal plane, and you see that the wide field planetary camera is right in the center. It was considered the primary instrument. And then here are these fine guidance sensors, their field of view, and then the other 4 science instruments around here. Okay, I'm going back to this diagram, and this time I'm going to tell you how the fix was implemented. And for the moment, don't worry about the red squares. I'll explain what that's about. But let's just go through this again a little differently. So I mentioned that the camera, the job of the camera is to take the telescope image, which is produced here, and relay it to the CCD detectors. So here's the image plane of the telescope, and here's the image plane of this channel on its CCD. Okay, that's we talked about that. That is fine. At the same time, though, the camera forms an image of the primary mirror in the telescope on this relay mirror right here, this little secondary. So what that looks like is here's the OTA mirror, which is up here somewhere. Remember, the light from the telescope is coming down like this. And this surface where the primary mirror is located gets imaged right on this mirror. It became very clear to people when the problem with the primary mirror was discovered. They realized very quickly that, hey, we can correct this if we put the correction right here on this secondary mirror. That's the perfect place to do it. You have an image of the primary. So it's as though the primary mirror were sitting there in a very shrunk down dimension. And if you change or put in the appropriate curvature on this mirror, you can correct the aberration with the primary mirror. So that was the plan. Correct the primary mirror spherical aberration at this secondary relay. Now, again, with the nothing comes for free phrase, it looks easy and it makes sense, but there's a lot of engineering challenges. The first thing that becomes apparent is the image of the primary mirror has to be very well registered with the correction on this secondary. So think of it this way. Imagine you have 2 bowls that are nested. If they are lined up, if their axes are in line, then the 2 bowls fit together nicely. However, if you decenter one or displace one of them, they not only don't fit together, but one of them starts tipping, you get problems. And that's the same thing here. If the image of the primary mirror is not well registered with this mirror, you end up with worse optical problems than you started with. That alignment was determined to be about a few microns. This camera was never built, the original camera was never built for that kind of a tolerance. So parts of it had to be re-engineered. So I already talked about the secondary mirror. They had to change the curvature on it. The other things that had to be changed are in this red box. So the fold mirror here and the steerable became a steerable pickoff mirror had to be articulated in tip tilt so that they could align the image of the primary mirror, register it with this secondary mirror. So that all had to be engineered to make these articulating mirrors. The next issue was this fold mirror, the pyramid mirror, excuse me. It was determined that the repeatability, when you switch that mirror 45 degrees to go between the two imaging modes, the repeatability of the position of that mirror was not accurate enough for this registration here. So that had to be fixed. They took the rotation out of that. And let me just on this next slide list all the challenges, that the engineering challenges. The first thing, the original Wide Field Planetary Camera 2, the copy, was scheduled to be delivered in 1994. However, in 1990, when the problem with the Hubble telescope was discovered, they moved that up to a delivery in the summer of 1993 to meet a servicing mission in December of 1993. So that moved the schedule up. Meanwhile, those little secondary mirrors, and I'll show you on the next slide how small they are, had to be very accurately shaped. And so they had to start a whole process there, get those mirrors fabricated, they're very small. They have a lot of curvature in them. They're very far from spheres. So this was a problem. The decision was made to only include 4 channels. Remember, there are 4 wide field and 4 planetary. Instead of having 8, they said, we're going to only have 4. What we're going to do is we're going to have 3 wide field channels and 1 planetary. And I'll show you in a second what that looks like. That was done to save cost, to save schedule, because the schedule was moved up. They had to save costs because they now had to articulate mirrors that previously had not been articulated. And because they were only going to use these 4 channels, they were allowed to fix the pyramid mirror, which reduced risk. So those were the engineering changes that had to be made to the camera. But fortunately, you see, they didn't have to make major displacements of elements. They didn't have to restructure the basic layout of the camera, which was a good thing. The final thing, which you may not think about, is now that this camera is designed to work with an aberrated wavefront coming in from the telescope, it's hard to test, because if you put a good wavefront into it, it's going to produce a lousy image because it's aberrated. So the only way to test it is to have a source, which we call the stimulus, that produced a wavefront that looked like it was coming from the Hubble telescope. In other words, it had to have the exact amount of spherical aberration. Then when you put that into the camera, the 2 things which are individually aberrated should produce a good image. So that had to be done. And here's that mirror that carries the correction. Remember, the primary mirror is 2.4 meters across, and it gets imaged on this mirror, which is not much bigger than a penny. And that's where the correction went. NASA had some serious doubts that they could keep the image of the primary mirror registered properly to a few microns on this mirror, but eventually they were convinced. The project moved forward, everything was done. And this is what now the field of view of the camera looks like on the sky. There are 3 wide field channels that have their 800 by 800 CCD like that. And then in the one corner, they removed one of the wide field channels and put in the planetary channel. So why did they do that? Well, this gives them a compromise. They can still have a pretty wide field of view, yet if they want to see something in more detail, they can put that object in this location where the higher resolution planetary camera channel is. And here's the result. Here's an image. This is probably the most iconic image that Hubble's ever produced. It's called the Pillars of Creation. You see it everywhere. It's been used in advertising. You see it all over the place. And you'll notice this is exactly the pattern. There's this black area here, which maybe people think, oh, something bad happened there. Well, not really. It's just that this quadrant, they use the higher resolution relay, and therefore you see a smaller patch of the sky. So if you ever see an image that looks like that, it's not really a mistake. It was planned. Okay, that fixed the wide field planetary camera. What about the axial instruments? Well, while JPL was working on WIFPIC 2, Goddard Space Flight Center came up with a fix for the axial instruments. It's called the Corrective Optics Space Telescope Axial Replacement, COSTAR. You'll never hear this whole title. It's always COSTAR. So it's important to have a clever acronym. And what COSTAR is a telephone booth size instrument that has a bunch of little dental size mirrors in there. And it does the same thing that the wide field planetary camera does. It corrects the aberration from the telescope before it feeds them into the science instruments. So COSTAR was installed in the space that was formerly occupied by the high-speed photometer. And so here's what that looked like. In the 1993 servicing mission, you see the new WIFPIC camera going into the telescope. You see COSTAR being installed where formerly they had the high-speed photometer. And so both installations were done over a 4-day period. This was an extraordinary mission with many, many hours of extravehicular activity, which had never been done before. Nobody knew how well this was all going to work. And here's how well it worked. So on the left, you see a typical image of this star field area of the sky with a ground telescope. Of course, it's blurry because it's looking through the atmosphere, and you're looking at very high magnification. This has got 0.6 arc seconds of resolution, which is pretty good. But the idea of going to space is to get above that atmosphere where you can get much better resolution. Here's the original images produced by the WIFPIC camera before it was fixed, or the telescope was fixed. And then we've talked about this image. And here's after the servicing mission. The camera now met all of its specifications in optics speak. The images were diffraction limited. So it was an unqualified success. The camera, the Wide Field Planetary Camera 2 with that correction was in Hubble for 15 years. It worked without any flaws. After 15 years, it was removed in favor of an upgraded camera, and it now resides at the Air and Space Museum in the Smithsonian Institution. So in the last few minutes, let me quickly talk about a science result. The science return from Hubble is pretty overwhelming. There's been over 1.5 million observations, 19,000 scientific publications. Hubble is arguably the most productive astronomical instrument ever built, still going, by the way. And I should mention at this point, it was built for a 15-year mission. And now we're on almost 33 years. April will be 33 years since it's been launched. So it's exceeded its expected lifetime by a factor of 2 and is still operating. So I want to look at one science result that was a complete surprise. They had, of course, a whole list of things they wanted to do, but they also did some other things that are just kind of, what the heck, let's do this and see what happens. That's called the Hubble Deep Field. And you've probably, or many of you, I'm sure, know all about this. So in 1995, the telescope took a long exposure of a part of the sky that was devoid of any known celestial objects. It was a black part of the sky. Of course, we're talking a very small part of the sky where there's not known to be anything. The exposure consisted of 342 separate images taken over 100 hours with a 10-day period. And that's one of the beauties of having electronic detectors, is you can just keep adding images on top of each other, and it's like you're making a very long exposure. This area of the sky is about 2.5 arc minutes on the side, which is approximately the size of a pinhead if you hold it at arm's length. And there are 22 million of these little patches required to cover the whole sky. So we're talking about a very small segment of the sky. And here's what the image, part of the image I'm showing that came back. So everything you see in this image is a galaxy. Incredible variety of shapes, sizes, colors, and of course the brightness is hard to judge because you don't know whether it's a close one or far. But anyway, just a myriad of galaxies in this very small patch of sky. The full image, when you count them all up, is about 3,000 galaxies. If you multiply that by the number of these little patches required to fill the sky and assume that one part of the sky looks like any other, which is one of the basic assumptions of cosmology, then you get on the order of 100 billion galaxies in the observable universe. This was followed up in 2003 and 2004, which was with what was called the Hubble Ultra Deep Field. This used a different camera, a more sensitive camera, because it was put in later, and a different part of the sky. So you took out all these things that could have been variables, new camera, new part of the sky, and the result was basically the same. This time around 10,000 galaxies were observed. So the conclusion, again, is there are somewhere on the order of 100 billion galaxies in the observable universe. So what's the implications of all this? Well, we have our 100 billion galaxies. If you assume that there are about 100 billion stars per galaxy, which is seems to be a reasonable number, then you get 10 to the 22 galaxies. That's a 1 with 22 zeros after it. And then if you make the final connection, we now know that planetary formation around stars is very common. If you just assume one planet per star on average, you get on the order of 10 to the 22 planets in the observable universe. And I'll let you draw your own conclusions about what that might mean for life in the universe. So with that, I want to thank you for your attention, and I guess we can take questions.
Dr. Robert Korechoff, thank you very much. And can I say, Tim and Grant observed that I've observed in the chat, this was the first time we've ever heard a detailed and coherent explanation. And your presentation was truly remarkable. Thank you very much.
Thank you. I just should add one thing. I know I put in a lot of detail, in which has good and bad, but it is nearly impossible to find all this stuff in one place. What you have to do is search through a bunch of documents and so forth and extract this and that. And so my attempt was to put everything in one place. And thank you for your patience going through all that.
Well, a remarkable discussion all in all. And I would invite everyone to turn on their microphones and turn on their videos. And I open the floor for questions. Please come forward with a question if you have one.
I have actually two questions. The first question is, what was the aspheric departure of the primary mirror compared with what was targeted and what was actually produced based on your optical prescription? That is the departure or profile from the nearest fitting sphere.
Okay, I actually was intending to say that, and I missed that. So here is a spherically aberrated mirror that could be like the primary. And you'll see that in this kind of a error, the maximum departure from what you wanted is at the edge.
Yeah.
Okay. It's actually basically 0 at the center, and it grows as the radio coordinate to the 4th power, but that's side point. At this juncture here, it was 2.3 microns. That's the surface error. So when the wavefront reflects off of that, it's actually double. But a lot of people, 2.3 microns. Now look at this, is a 2.4 meter mirror. And this is a 2.3 micron deviation here. So that's 1 part in a million. It seems like that shouldn't cause much problem. But in optics, what really counts is the size of the error relative to the wavelength you're going to be dealing with. So typically the middle of the visible spectrum is about 0.5 micron, right? So you double this and you see that that's 4.6 waves of error, which is just so out of sight. You know, normally mirrors, they talk about 10th wave or something like that, right? And here we have multiple waves of error. So the error is just plain enormous.
Thank you. The second question I had was the corrective mirror that went into the WIFPIC, the one you showed approximately the size of the penny. What was the method of fabrication?
Well, I could tell you where we've done it, Tinsley, which is up in the Bay Area.
Yeah.
Now, I don't know if they certainly had to be extremely careful, and Tinsley was known for making highly specialized optics. They wasn't a place that just cranked out, thousands of lenses. They did highly specialized stuff. They had done a lot of stuff for JPL. The actual fabrication methods, I don't know. Now, there is a person in the audience that actually put those relays together. His name is Jeff Osius. He still works at JPL. Whether he has something, knowledge of that fabrication technique, I don't know. Jeff, are you there?
Yeah, I'm here, Bob. Good afternoon, good morning, depending on your time slot. Yeah, Tinsley took a lesson learned from the initial error and created a set of very highly accurate null lenses. And we're able then to generate and polish those lenses using conventional techniques, but then did a lot of iterative testing to narrow down to the correct prescription.
I had heard somewhere, I thought that they were diamond turned. And
the blanks were diamond turned, but the final polishing could not be done diamond turned for these types of wavelengths.
because diamond turning will generally leave a surface ripple at some tiny scale. And for
Right.
something like that, I would expect it would have shown up over the entire aperture. So you must have post polished that.
Oh, correct. Absolutely.
Thank you.
Thanks, Jeff.
You're welcome, Bob.
Other questions, please? Anybody?
Was
Hi,
this
can you hear me?
primary mirror specifically poured for the Hubble telescope, or was it repurposed from
No,
other military missions?
it was specifically made for the Hubble, and at the same time, Kodak was making a backup. And the backup telescope was only carried so far. I'm not sure how far they went in the shaping of it, but they got it to a certain point, and it was intended to be put into use should something happen to the Perkin-Elmer mirror before it got into the telescope. Somebody drop a wrench on it, and then they had, instead of having to start over, they had another primary mirror partially fabricated. And as far as I know, that Kodak mirror, I don't know if it's been reused. It's either been reused or it's still sitting in a warehouse somewhere in Rochester.
Those mirrors were not poured in the sense of pouring molten glass. They were fabricated by a procedure rather like welding. There was a face
Right.
sheet and there was a rear sheet, and then
Yeah.
they built up these slats of the inner core using this welding technique, and then they fused them together.
Correct. And that was the whole idea of lightweighting it. Exactly. To have that honeycomb core.
Grant, you had a question you want to step in and ask it?
Yeah, can you hear me?
Yep, I can hear you.
Okay. Hi. Thank you, Robert, for that excellent speech. That was, as Steve said earlier, information that we'd never seen in one place before. That was a great effort to gather it all, and we do appreciate that very much. I have one really simple question. It would seem that if the optical issue had been correctable by modifying the secondary, then you wouldn't need to modify each individual instrument. Is there a good reason it wasn't approached that way?
Let's see. I'm not, don't quite think I followed it. The correction on that secondary mirror was for the wide field planetary camera only. Okay, so that the light came from the telescope, the pickoff mirror directed it into the camera.
No, okay.
I'm sorry. Did I misunderstand the question?
What I was saying was the Hubble main optics is a primary and a secondary, then
Yes.
there's all the individual instruments. And the issue was with the primary mirror.
Yes.
Could that not have been corrected by modifying the secondary?
Oh, okay. So but what you're suggesting is actually similar to what another suggestion was let's go up with the space shuttle, capture the telescope, bring it down to the ground. Let's replace the aberrated primary mirror with this Kodak mirror, get that one finished, and then relaunch it. And I think what you're suggesting is it would have required bringing the telescope down. I don't think they could have done that replacement on orbit. Even though the secondary mirror is, is relatively small, it means kind of ripping apart the whole observatory. And there was the cleanliness issue within the cargo bay of the space shuttle. So I think repair on orbit was immediately ruled out. I think, I know that bringing it down was ruled out for a couple of reasons. Number one, nobody knew whether the space shuttle could actually land fully loaded. They knew they could launch this load, but it was never clear whether they could bring it down fully. That had never been done. That was concern number one. Number two, as I just mentioned, it's a huge job to strip this whole thing down and replace the primary mirror. That would have taken a long time. And then you had to load it back in and put it back on orbit. That's 2 shuttle missions required. Each shuttle mission is hundreds of millions of dollars. So there was an enormous financial hit to bring the telescope down. And quite frankly, because of the funding issues that Hubble had faced over the years, nobody was confident that if they brought the telescope down, it would ever go up again. That Congress would just say, no, that's it. You guys screwed up. Too bad. So they were desperate to find a solution that did not involve replacing the telescope, because those mirrors were hard to get at, that involved the instruments and could be done on orbit.
So basically the secondary was never meant to be serviced in orbit.
Correct. That
Okay.
is right.
Thank you. Scott and Jeff, you had some discussion about CoStar. Want to
Uh-oh.
jump in and ask about that, please?
Please take it away.
Yeah, I was just curious. I knew but have forgotten who developed the CoStar,
I will
not
do
Goddard,
that
but the
right now.
subcontractor that did the work.
I'm going to have to plead ignorance about CoStar. I know very little about it. The guy who came up with the idea is a guy named Crockett from Goddard. Supposedly figured this out in the shower, he always claimed. But anyway, I don't know who built all the specialized mirrors and who built the instrument.
Okay.
If somebody in the audience knows, please speak up.
I think they were in Denver, and I just kind of forget the name.
Oh, well, could have been Ball then.
Yeah, it probably was
Denver
Ball.
Aerospace is in
Yeah,
Boulder, Colorado, and
That's who it was. Thank
Okay.
you.
in fact, now that you mention it, that does sort of sound familiar.
Right.
Thank you.
And the other question I had was the process for the primary, developing the primary mirror was developed on another government program, wasn't it?
The process,
The sandwiching and the honeycomb and all that.
there were related government programs to the Hubble, but can't speak about those.
Got it.
Mike Burton, I thought I saw you jump in there. Did you have a question?
Wasn't me, Steve.
Okay. Then can I ask one? Of course I can. Here at the observatory, we have a number of myths and legends we tell. Well, they're intended to impress the public with all that has been done and accomplished at Palomar Observatory. And we recognize that perhaps some of these myths and legends may not always be true. Well, one thing came up during your discussion: the four-faceted pyramid mirror. And that suggested something to me that relates to a device called four-shooter. Famous here as supposedly that is the first astronomical telescope to use CCD detectors. James Westphal and Jim Gunn. And we are told, and we repeat this to the public without knowing it's true, but we were told that four-shooter was the prototype for WIFPAC 1. Is there any substance to that?
Well, let me just say, first of all, that WIFPIC, the original WIFPIC was designed before my time, even at JPL. But Jim Westphal, who you just mentioned, was the principal investigator for Wide Field Planetary Camera 1. Therefore, I think it's highly likely that this whole concept of being able to stitch images together and have these four different channels, it seems very logical to me that he tried it out on the ground before it was going to be tried out in space. So there's that. It looks like there's a lot of overlap that's probably more than coincidental. But I can't swear to it.
Well, that's very helpful. It just in the description of WIFPAC 1, this four-faceted pyramid.
Yeah, Westphal would have been the guy who wrote the proposal, the original proposal for this instrument to be included on Hubble. So he's the guy.
That's more that helps. Thank you very much. Richard Engler, you had a question. You want to step in?
I do, and thank you very much. I'm an amateur non-scientist here. My question is about the number of galaxies. If I'm not mistaken, I recall reading in the last, I want to say 3 to 5 years, that the estimated number of galaxies was revised upward from maybe 100 billion to somewhere in the low trillions. I know I read that in some legitimate source somewhere. Can you address that? What might I have encountered, and how legitimate might it be, etc.?
Yeah, I must admit I don't know any specific source that said that. And I don't keep up as much as I should on the current literature. It wouldn't surprise me that even the ultra deep field that was done in 2003, okay, that's already 20 years old, and there's been enormous advances in observation and instrumentation and even theory. So I can't say yes or no to that number, but I would say it wouldn't surprise me that there's been a lot of change in those estimation.
Thank you.
Sorry, I can't give you a better answer.
Appreciate it.
Remember that those numbers that come from the Hubble images count the number of galaxies that it can see. And there are a lot of galaxies, especially dwarf galaxies, that it can't see because they're too dim. And that's a number you can play around with pretty free-handedly and come up with 1 trillion or 2 trillion or however many galaxies you really need to fit whatever philosophy of the universe you're working with. And so that few 100 billion galaxies or 100 billion is a minimum the number of galaxies you can see. Of course, if you tried to repeat the Hubble Deep Field exercise over the whole sky, I think I calculated once that it would take you something like 13,000 years of exposure time. It's probably not going to happen anytime soon. So yeah, the number of galaxies in the universe is something you can pretty much make up and get away with one way or another.
Yeah, so while we're talking about the deep field, Webb has repeated that. I don't know what the number is, but and a number of other measurements have been made since the Hubble measurements. And the other thing I would say about these kind of numbers, these huge numbers, I mean, if you're off by a factor of 2 or 3, that's the same as being perfect. I mean, these numbers are just not known that well. So you talk about orders of magnitude more than whether it's a factor of 2 or 3. So 100 billion going to a trillion is an order of magnitude that would require, I think, some additional evidence. But if you went to 300 billion, nobody would blink.
And David Shepard wanted to know what material the honeycomb is made of.
I'm guessing it's the same thing, the ULE. It would make sense to me that you want the material to all be the same. So even though it's not supposed to change with temperature or change very little, you're attempting to make it as homogeneous as possible by using all the materials. So I don't know that 100%, but that would be my guess. If somebody knows for sure, they could chime in. But I would say ULE for the honeycomb.
Thank you.
Do we know why the secondary mirror was not made out of the same ULE as the primary, but was made of 0?
I was wondering if somebody was going to ask that. I have not been able to discover the reason. They were both made by Perkin-Elmer. It may have been just they wanted to spread the wealth around to 2 different companies. I don't know. As I said, ULE is a Corning product, and Zero Doer is a shot glass product, and maybe they wanted to keep both contractors happy, or both companies in the game. I don't really know. I always found that a little surprising. And maybe it was a schedule issue. You know, the amount of maybe this guy said, I can only do one in the time you need it, and the other guy said, oh, I can do it. Those are all possibilities, but I don't know definitively.
We've got to start winding down the meeting. We're running a little long here.
Well, I have a suggestion, Steve. I see there's 17 items in the chat box. What I would be willing to do if you send me those questions from the chat box, and I'll try my best to answer them and send them back to you, and then you can send them out to the people who asked the questions. Would that be agreeable?
That's agreeable. And with that suggestion will let us bring this meeting and this question period to an end. This has been a wonderful session. Thank you very much. Well, I greatly appreciate it. And I think everyone is really impressed with the discussion today.
Well, thank you all for participating. I appreciate the attention and the excellent questions.
And with that, let me have a word about our next meeting in 2 weeks. The Greenway Talks online will continue on Saturday, February 4th, when Timothy Thompson of Mount Wilson Observatory will give a presentation titled Stellar Evolution and the Origin of the Elements. Tim, thank you very much for participating in and contributing to the Greenway Talks online.
Yeah. Thanks for asking me to talk. I like to talk, especially too much.
Oh, I hadn't noticed. Oh, I'm sorry. No, but really, thank you for stepping in on this. Casey Law was scheduled. He had to cancel. He has rescheduled for March 4th. talk on fast radio bursts. And on February 18th, Professor Ari Loeb will talk about messengers from alien civilizations. That's our schedule right now. Again, thank you to Dr. Robert Korechoff, and my thanks to all of you for attending and supporting the Greenway Talks online. I'll close the meeting. See you again on the 4th. Thank you and goodbye.